Today's lesson is on valence electrons, and from those valence electrons be able to drawing Lewis dot structures of an element, and from there be able to use the electron configurations that we've already learned about to determine which of the electrons in the electron configuration are the valence electrons. Okay, so here's our objectives. We're going to determine what the valence electrons are and how to determine them from the periodic table. We're going to be able to draw Lewis structures to show the valence electrons. And when we use our electron configurations, we're going to be able to show which one of those electrons in the electron configuration are the valence electrons. Remember, valence electrons are important because we need them to understand how an element bonds with other elements. The valence electrons are the ones that are involved in the bonding. So understanding what the valence electrons are, where they're located, gives us an insight onto chemical bonding. You may already know this, but this is just a quick definition and review of what are valence electrons. Valence electrons are the electrons in the most outer energy level shell. Valence electrons are the ones that are involved in chemical bonding. We've already mentioned that. Understanding where an atom's valence electrons are, the energy level and the sublevels, and their number provides insight into the atom's ability to bond. The maximum number of valence electrons is 8. So you won't have any more than 8, you won't have any less than 1. There is no such thing as 0 valence electrons. So the number is in between 1 and 8. The periodic table tells you how many valence electrons an atom has based on the grouping that the element is in. So it's very straightforward. In group 1, this group right here, which is the alkali metals, all the alkali metals have a valence electron number of 1. In group 2, which is our alkaline earth metals, all the valence electrons are the same. They're 2. Every alkaline earth metal will have 2 valence electrons. Skipping over the transition elements, they can have multiple valence electrons. We're not worried about them yet. Going to group 13, every one of the elements in group 13 has 3 valence electrons. Group 14 has 4, 15 has 5, 16 has 6, 17 has 7, and 18 has 8. Now here's the valence electrons right here, right? And you can see that there's a pattern, right? 1 and 2, 3, 4, 5, 6, 7, 8. So when you're above 10, you're going to just subtract 10 from the group number, and that will tell you how many valence electrons. So for example, group 13, subtract 10 from that, you get 3. Group 14, subtract 10 from that, you get 4. The increasing number of valence electrons goes from left to right or across a period. And again, remember, all the groups have the same number of valence electrons, even though the element here, for example, oxygen and sulfur, differ by 1 period or 1 energy level, they still have the same number of valence electrons. We will use these things called Lewis dot structures to represent the number of valence electrons. Lewis dot structures show the number of valence electrons via dots around an element symbol. Each dot will represent 1 electron. The maximum number of dots is 8. So let's look at a couple of examples here. Example 1 is francium. Now francium is an alkali metal, and therefore it would only have 1 valence electron. It's represented by 1 dot. Aluminum is in group 13, so remember the rule is if it's more than 10, you're going to subtract 10 from the number, so group 13 becomes 3, and it has 3 valence electrons. Oxygen is in group 16, it has 6 valence electrons. Each electron is represented by a dot. The chemical symbol is in the middle, and then we represent the valence electrons only, the valence electrons only by dots. So there's a pretty simple way to write Lewis dot structures for the valence electrons. And there's a lot more words on here than really how simple it is. You're going to write down your element's chemical symbol. Right, so you look it up on the periodic table if you don't know what that is. For example, iron would be Fe. Determine the number of valence electrons that your element has. Remember, period groups tell you the number of valence electrons. Subtract 10 from groups 13 to 18 to give you the number. So I've got a little table here. Group 1 has 1. Group 2 has true. So all the elements in group 1 will have 1 valence electron. All the elements in group 2 will have 2 valence electrons. We skip over the transition elements, and now we're in group 13. Remember I said here, subtract 10 from the group number to give you the valence electrons. So 10 minus, 13, 10 minus 13, 10 from 13, it gives me 3. 14 minus 10 gives me 4. 15 minus 5 gives me, 15 minus 10 gives me 5. 16 minus 10 gives me 6, etc., etc. You're going to put an imaginary box around the element symbol and place the first electron on one side of the box. I'll show you what that means in a minute. If there is a second electron, it goes to the next to the first one. Each side can get a maximum of 2 electrons. You can't have any more than 2 electrons per side of your box. Remember, your box is 4-sided. Any other electrons get put around the box sequentially, one aside until you need to double up. Remember back to the electron configuration when we talked about the arrows, right? You have these suborbitals like this, and then you have to put one arrow in, one arrow up before you double back. That's exactly what you're doing for the electron configuration. For the Lewis dot structure. Except instead of using arrows, we're going to use dots, and except of using the little lines on the bottom to represent the orbital, we're going to use the side of the box. Okay, so let's look at a quick example here. Let's pick the element of chlorine. Chlorine is group 17, so we subtract 10 to give us 7 valence electrons. Rewrite the chemical symbol for chlorine. Rewrite the first 2 electrons on one side of the chemical symbol. Right, so here's my first 2 electrons right here. We just wrote them here. Electron 1 and electron 2. Fill the remaining 5 electrons sequentially around the chemical as shown by the numbering pattern. Now this numbering pattern is not fixed, right? You could put 3 here. So you can put 3, 4, 5, 6, 7, 8. Remember, we're going to put 1 aside until we have to double them up. So the first one goes here, then the next one goes here, then the next one, then we start doubling up because we ran out of sides. And then 8. Remember, first 2 together, they're going to represent our S sublevel electrons. Remember how they filled that up in the electron configuration. The S level filled first before we went into the P level. And all these electrons are in the P sublevel. And remember, we filled the P sublevel. Let me just draw that real quick. Remember, we had the S, and then we had the P. Remember, we put the 2 electrons in here. It doesn't matter what energy level you're in. Then we went to the P to do this, but it's exactly what we're doing here, right? 1 electron here, there we go. 1 electron here, there we go. 1 electron here, there we go, right? Each one of these is going to represent the side of the box. Here's my first side, here's my second side, my third side, my fourth side. All right, so we just go around the horn basically, and write the rest of the electrons. All right, so first 2 go here, then we have 3, 4, 5, 6, 7, 8. Okay. So my finished dot structure will look like this. Notice that there's 1 dot missing, right, because it only has 7, so there's an empty spot where another electron could finish. Okay. Simple as that. Now we're only concerned about the correct number of dots. Right, the correct number of dots are important, not the start side. So remember, I told you to put the first 2 electrons on the start side. You could put the first 2 electrons here, 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 or here, depending on which way you want to do it. Right? There's no right way for any of these. These are all equivalent. All of these are equivalent. Right? This one is just as equivalent as this one, which is just equivalent as this one, which is just equivalent as this one. As long as you have 7 dots for chlorine around, and one of the dots has an empty spot, and the other 3 sides are filled with 2 electrons, it doesn't matter which side you start your numbering from. So you could have said that this be number 1, and this is number 2, 3, 4, 5, 6, 7, whatever. As long as you have it look like this in some manner, that's the important part. All are equivalent regarding a Lewis dot structure as long as you have the correct number of dots. Okay, before I let you guys do it on your own, let's do some guided practice here. So our first element is boron. Now boron is in group 13, but as I mentioned before, you have to subtract 10 because we're above 10, and to get the correct number of valence electrons. So 13, subtract from that 10 will give us 3. So we put boron here, B, and we have 3 electrons. So I'm going to put 2 on the one side, as I always do, and then I put 1 there. Bromine is in group 17, so subtracting 10 from 17, I get 7, so it has 7 valence electrons. And the chemical symbol for bromine is Br. And again, we put our first 2, then we put our single, 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 double, double, and we left with the empty spot on the bottom here. Looks very close to or similar to chlorine, and it should because chlorine is also in group 17. Lithium is in group 1, so it has 1 valence electron. It's an alkali metal, so we have 1 valence electron. Neon in group 18. 10 from 18 gives me 8 valence electrons, so I'll put neon as the chemical symbol is Ne, and put 2 valence electrons around each side. Now you just notice I didn't do the normal pattern like I've done before because I know they're going to be all filled up, so there's no way that I have to worry about going in sequentially. Calcium is in group 2, so we put the symbol for calcium, and we have 2 electrons in group 2. Aluminum, group 13 again. Subtract 10 from 13 to give me the valence, and we have 3. So again, we have put 2 electrons on one side, and then 1 here. Oxygen in group 16, subtract 10 from 16 to get me 6 valence electrons. Put my first 2 on one side, and then we're going to start putting them single first. 1, 2, 3, 4. Remember, all these little, while we're doubling them up, these means that they're pairs of electrons, right? These are pairs of electrons, and they're in specific orbitals. And then the last one is nitrogen. Nitrogen is in group 15, therefore it has 5 valence electrons. The chemical symbol for nitrogen is N. 2 dots first, 1, 2, 3, and there you go. That's the end of that. So you've got a good example of how all this was done fairly quickly, and you should be able to do it now on your own. Okay, so now you are going to try to do it on your own. So you're going to copy these names down on a piece of paper when you're ready, and then you're going to stop the video and give yourself some time to complete it. When you're finished, you're going to restart the video, and I'm going to give you the answers. So when you're ready, stop the video now. Okay, so I've given you the answers for each one of the ones. Again, your answers may look slightly different depending on which side you put your electrons. I usually start on this side just for giggles and grins, but you definitely can put electrons anywhere. Here's the time I started with the electrons on the bottom. All right, I usually start with the electrons, the 2 electrons on the right-hand side representing my s orbital. The other ones are representing my p. But again, there's no right way to do this as long as you have the correct number of dots and they are correctly paired and not paired. So for example, phosphorus, you must have 2 dots that are next to each other and then 3 single dots. Carbon must have 2 dots and then 2 single dots. you sometimes will see carbon written like this, right? And that's an accepted way because of the way it bonds, but for our class, we are going to only do this way, right? Right, so this way is out, right? It's not that it's wrong per se, but it's not the convention that we're typically going to use. Again, silicon and carbon look the same because carbon is above silicon in the periodic table. Okay, so we spent a lot of time writing and understanding electron configuration previously. So let's see how the electron configurations can actually tell you the number of valence electrons and in what energy level they're in. So I've given you here the first 18 first 18 elements in the periodic table and the corresponding electron configuration. Now I also said to you, remember, electrons, the valence electrons are the ones in the highest energy shell, right? The S&P in the highest energy shell. They are not located anything below that. So if you see, for example, let's just pick an element here. Neon is in the second energy level. The electrons that are in the first energy level are not valence electrons because they're buried, right? They're underneath the second energy level, and the second energy level has electrons in it, so therefore they're the ones that are the valence electrons. So let's count them real quick to show you how this works, right? So my first element is hydrogen. It only has one valence electron, and that's it right there, right? And then helium has two valence electrons, and they're there. Now remember, we go up one energy level, and so these electrons no longer in the first no longer the outermost energy level, so it's only one here, right? And then now we have two, right? Remember, these electrons don't count; they're underneath. Now let's look at boron. Boron has how many electrons in the second energy level in the S&P? We have 3. We have 2 here and then 1 here. And what is the valence number for boron? 3. Carbon, we have 2 and 2. That's 4, etc., etc. Now look at neon. Neon, we have 2 and then 6, so that's 8. All right. Let's jump up a couple, right? What's under carbon? Remember, carbon is here. Here's my carbon. It says it has 2s2, 2p2, right? Let's go to silicon, because that's right underneath carbon. Okay. Now, remember, all the electrons that are below the outermost energy level don't count as valence. So the 1s is gone, the 2s is gone, the 2p is gone, and we're only left with 3s and 3p. And if you look here, those are 4 valence electrons. And we could do the same thing for example chlorine. Let's look at chlorine and fluorine. Here's my chlorine. How many valence electrons does it have? Well, the 1s is below the 2s, and the 2p, and therefore the 3s, 3 and 3p are the only ones there, so we circle those. There's 7. Let's go to fluorine. Fluorine, the 1s is buried, but the 2s is the outermost energy level, and if we circle those numbers, that gives us 7. So that it lines up, right? Chlorine and fluorine are in the same group. Carbon and silicon are in the same group, right? Lithium and sodium are in the same group, and they all have the same number of valence electrons. So they match, right? And you're only looking at the highest energy level. In this case, it would be the 3rd. Everything else below it is buried. In this case, it would be the 1s because that's the only energy level you have. But in this case, in beryllium, the 1s is now gone. We have 2s2, so it has 2 valence electrons. So that wraps up the quick tutorial on valence electrons, electron configurations, and writing Lewis dot structures. If you have any questions, you can find me in class.